Good morning. Now, today we will begin our second semester portions. So, in that, I will be teaching you Unit 2 Integral Transforms from the paper Mathematical Methods in Physics. In that unit, you will learn about Fourier series, Fourier transform, Fourier integral, Laplace transform, then inverse Laplace transform, and so on. So it's a little bit lengthy unit. So what I'm planning to do is I will give you the concept, that is the theory of each of these portions. So today we will learn about Fourier series. So I will brief you the concept, the theory behind what is Fourier series, etc. And for exams you will be asked to solve problems related to it. So after taking the theory of each portion, I will try to present one or two problems. Okay. But in this limited time I won't be able to work out all the problems, so the rest problems I will upload in LMS as PDF file, so you can download it and work out. Okay. So a few problems, sample problem 1 or 2 I will work out during the presentation, and similar problems I will upload as PDF file, solved problems, so you can work it out. So one more thing, don't get satisfied with what I am giving, because in a limited time we won't be able to present everything in the class. So you can refer uh, some of the reference books that is mentioned in your syllabus, and try to work out as much as problems you can, because for exams you will be asked problems. Okay. So in the for reference you can choose Mathematical Physics by Satya Prakash. It is easy to follow, at the same time other you will get a lot of problems. Okay. So just go through the class that I'm taking, go through the problem that I'm working out during the class, and then go through the problems that I am uploading as PDF file, and then you try to work out more such similar problems from the so-called reference book. Okay. That will be easy for you. Okay, that's enough. So for today, we will begin our session, which is about Fourier series. J.B. Fourier in 1822, he published Fourier theorem just to analyze complex periodic functions. It states that any complex periodic continuous function, say f of x, can be expressed as a series of sine and cosines in the form given by equation 1. See, this is a complex periodic continuous function f of x. It is expressed as a sum of cosine and sine functions. So this equation 1, this one is your Fourier series. It is represented in the form f of x is equal to a0 plus sigma n from 1 to infinity a n cos n x plus sigma n from 1 to infinity b n sin n x. Okay. Now this function f of x is said to satisfy a Dirichlet condition. Uh, Dirichlet conditions are mentioned in 2 points. One is that the function must have finite number of maxima and minima. Then the function must have finite number of finite discontinuities in a period of one oscillation. So when you are asked to write what is Dirichlet condition, you can specify these 2 points. Okay, so any Fourier series has to satisfy the given 2 conditions called Dirichlet conditions. Okay, now in equation 1 you can see a0, an and bn. They are called as Fourier coefficients. Okay, so equation 1 is the Fourier series, then a0, an and bn are the Fourier coefficients. So for your exam you will be given a question and you will be asked to find the Fourier coefficient, that is a0, an and bn. Okay, so for that we have to find out a formula to calculate these Fourier coefficients, say a0, an and bn. So let us do that. Before that, just note this orthogonality property of sine and cosine function. One is the one given by equation 2, then that is minus pi to plus pi, sine mx cos nx dx is 0. So whenever you come across this integral, you can put it as 0. Okay, why? as per orthogonality property, it is like that. Okay, no need of proving. So whenever you come across this type of statement, that is minus pi to plus pi, sin mx cos nx dx, no need of evaluating it, you can put it as 0 because as per orthogonality property. Now next one, minus pi to plus pi sin mx sin x dx is equal to minus pi to plus pi cos mx cos nx dx is equal to pi delta mn for mn not equal to 0. Now this one will reduce to 0 for m not equal to 1, and this will reduce to pi for m equal to n. So these are the orthogonality property which you will have to make use while deriving the formula for getting a0, an and bn. Okay, so please keep in mind this orthogonality properties. Now first let us evaluate the first Fourier coefficient a0. For that, you just integrate our equation 1. What was our equation 1? F of x equal to a0 plus sigma n from 1 to infinity an cos nx plus sigma n from 1 to infinity bn sin x. Sin nx. Okay. So you just integrate equation 1, that is LHS and RHS of equation 1 between the limits minus pi to plus pi. Okay. So it will look like this. Now here this integral, that is a0 integral minus pi to plus pi dx. What is it? Integral minus pi to plus pi dx. Integral dx is x. Now apply the limit minus pi to plus pi. It will be pi minus minus pi. So it is 2 pi. So the first one reduces to a0 2 pi. Okay. Now what about the second one? This integral minus pi to plus pi cos nx dx is 0. So this term will reduce to 0. Okay. Now this one, this minus pi to plus pi sin nx dx, it is 0. So this term also will become 0. So you are left with a0 2 pi, that is minus pi to plus pi f of x dx is a0 2 pi. From that a0 is equal to 1 by 2 pi integral minus pi to plus pi f of x dx. So that is your formula to calculate the Fourier coefficient a0. Okay. Now let us see how to evaluate an, the second coefficient. For that, again you take equation 1. Now multiply LHS and RHS of equation 1 with cos mx, and then you integrate from minus pi to plus pi. So by doing this, it will look like this. Okay. Now here again minus pi to plus pi cos mx dx is 0. So this term will reduce to 0. Now what about the next one? This one. Okay. Here an is kept as such. Now this one minus pi to plus pi cos mx cos nx dx, as per orthogonality theory it is pi delta mn. Now here we are supposing this delta mn as 1. So delta mn is 1 only when m is equal to n, right? So this will reduce to delta mn, you take it as 1. So this an will now become am. Why? Because delta mn is 1 only when n is equal to m. So you just replace an as am. Pi is kept as such. Okay. So it will be then this one is again 0. So as per orthogonality property, so this is 0. So you are left only with am pi. So these two terms get 0. Only you are left with this term. Here an is kept as such. Then this one, as per orthogonality property, it is pi delta mn. You are assuming delta mn as 1, and that will occur only when m is equal to n. So you will write as an pi. This you can assume an. Instead of n, you must write am pi because you are assuming delta mn to be 1. It is 1 only when n is equal to m. So you just write instead of an, am pi. Okay. So what is left? This one has now reduced to am pi. So am pi will be this one. And after that, in order to reach the normal form, again replace this m with n. So you will have the formula for an as 1 by pi minus pi to plus pi f of x cos nx dx. Now similarly, you can find Bn also. For that, the only difference is that you have to multiply LHS and RHS of equation 1 with the sin nx, sin mx. In the other case, it was cos mx. Now it is sin nx. And then integrate from minus pi to plus pi. So it will look like this. Then the first term as such, minus pi to plus pi, sin mx dx becomes 0. So the first term is 0. Again, minus pi to plus pi, sin mx cos nx dx is again 0. So this term also reduces to 0. Now what about this one? Bn is kept as such. Now apply orthogonality property here, that is pi delta mn. Then that is written as such. Now Bn pi delta mn is here. Now make delta mn equal to 1. That is happening only when n is equal to m. So you must replace Bn as Bm. So it will be Bm pi. Okay, from that you can find Bm as this. Now again, to reach at the normal form, just replace m by n. Finally you get the formula to calculate Bn as 1 by pi minus pi to plus pi f of x sin nx dx. Okay, now we are just summarizing. So the coefficients given in equation 4, 5 and 6, as already said, it is Fourier coefficient. So if you have a Fourier series like f of x equal to a0 plus sigma n from 1 to infinity a n cos nx plus sigma n from 1 to infinity b n sin nx, the Fourier coefficients are a0, an and bn, and we have obtained the formula to calculate each of these Fourier coefficients, which are they: a0 is equal to 1 by 2 pi minus pi to plus pi f of x dx, an is equal to 1 by pi minus pi to plus pi f of x cos nx dx, and finally bn is equal to 1 by pi integral minus pi to plus pi f of x sin nx dx. So here always don't get confused. For an here it is cos nx, for bn it is sin nx. Okay, so study this formula very well. Now this I think you have studied in your lower classes, even function and odd function. We know a function f of x is said to be even or symmetric if f of minus x is f of x. Okay. Now here the graph of an even function is symmetrical about x equal to 0. That is, the graph on y-axis is the mirror image about x equal to 0. Now the area under such a curve from minus pi to plus pi is twice the area under the curve from 0 to pi. It is nothing but, if you have a function f of x and suppose that it is even function, then that function's integral from minus pi to plus pi will be equal to twice integral 0 to pi f of x dx. This is only in the case of even function. So if the given function is an even function, then how will you find the value of a0, an and bn? Okay, the formula will change accordingly. If the given function f of x is even, then how will you calculate a0? You know a0, the formula to calculate is this one, right? 1 by 2 pi minus pi to plus pi f of x dx. But here the given function f of x is even. Okay, so what is about this minus pi to plus pi f of x dx? As just mentioned above, it will be twice 0 to pi f of x dx. 2 and 2 get cancelled and you are left only with this. So if the given function f of x is even, the formula to calculate a0 is 1 by pi integral 0 to pi f of x dx. Similarly, the formula to find an is this one, and bn there is no need to find out, it will be 0 for an even function. Okay, so how will an even function look like? See, if this is your Fourier series, then for even function there is no bn, right? So what are the terms left in the Fourier series? It will be only this. There is no sine term. Why? Because bn is 0, so there will not be sine term. Okay, so this will be the form of an even function. That is, it is having only cosines. So it is also called by the name cosine series. Okay, now a0 and an, you can find it out using this formula. Bn is 0. Now similarly, just the contrast of even functions, the odd function. A function f of x is said to be odd if f of minus x is minus f of x. Now in this case, if if f of x is an odd function, then its integral from minus pi to plus pi will be 0. But in the case of even function, what was it? It was twice integral 0 to pi f of x dx, right? Okay, now just apply this. If the given function is odd, then a0 will be 0. No need of calculating. Okay, then an will be 0. An is 0 means there is no cos term there. Okay, now the formula to calculate bn will be this one. Okay, so if this is the series for a node function, this one is 0. This an is also 0. So these two terms goes off and you will have only this function. That is, you are having only sine term in the case of odd function. So it's called sine series. Okay, then bn, the value of bn is this one. An and a0 is 0. So just compare and study. For even function, what was it? You have formula to find a0 and an, but bn is 0 and you are having only cost function, so it is called cosine series. Okay, but in the case of odd function, there is no value for a0 and an. You have formula only to calculate bn and you are left with the sine function, so it's called sine series. Okay, now let us work out a problem. This will be similar problems will be asked. Find a Fourier series of the function. The function is given f of x. Its value is 0 when n is between minus pi and 0, and its value is k when n is between 0 to pi. So first of all, let f of x be represented by the Fourier series. So just write the Fourier series that we have studied. What is it? F of x is equal to a0 plus sigma n from 1 to infinity an cos n x plus sigma n from 1 to infinity bn sin n x. Okay, now let us start to find the values of Fourier coefficients, say a0, an and bn. Once you obtain all these coefficients, you can just substitute those values of a0, an and bn in equation 1. Let us begin with the calculation of a0. What is the formula? 1 by 2 pi minus pi to plus pi f of x dx. Okay, formula to find a0. Okay, then now write 1 by 2 pi. Here you have to split f of x. The integral is from minus pi to plus pi. So here you have to split it from minus pi to 0 and 0 to pi as per the question. Okay, from minus pi to 0, f of x is having value 0. Okay, so that we are writing it here. Then in the other one, in this limit, f of x is having the value k. Then integrate. On integrating, you will get the value of a0 as k by 2. I am not explaining it because these and all are simple integrations. You can work it out. So a0 is k by 2. Now what is the next formula to find an? Formula is 1 by pi integral minus pi to plus pi f of x cos nx dx. There is one term, right? Again 1 by pi is kept outside. Then split the limit minus pi to 0 and 0 to pi. In this limit its value is 0. In the here it is value is k. Cos nx is kept as such. Now after integrating you will find that the value of an is 0. Okay. Now at last bn. Again the value of bn is 1 by pi minus pi to plus pi f of x sin nx ds. Again you are splitting the limit and applying the value of that function in the appropriate limit, and you try to integrate. Finally you will reach the result as k by pi n 1 minus cos n pi. There is no much confusion in this integration. It is very simple. When you work it out, you will be able to follow. That's why I'm not explaining. There is no further complication. So you got the values of a0, an and bn. Okay, now here what is the value of a0? K by 2. An is 0. Now bn, here in the value of bn, see there is an n comes. N can be an integer, right? It can be either an even number or positive number, even or odd number. So you have to consider the both conditions here. That is, what is the value when n is even? That is, what is the value of bn when n is even, and what is the value of bn when n is 0. Why? Because in the final expression for bn you are having an n, okay, an integer. So let us see the value of bn when this n is even. Okay, when n is even, this particular term 1 minus cos n pi. Okay, here cos n pi will be 1. Okay, when n is even. So 1 minus 1 will be 0. So bn will be 0 if that n is even. Now if n is odd, then cos n pi will be minus 1. So 1 minus minus 1 will be 2. So 2k by pi n will be the value of bn when n is odd. So for when you write the final Fourier series, the expression, you just substitute the values of a0, an and bn. Here f of x is equal to a0. The value of a0 is now obtained as k by 2. So you just write it there. Plus sigma n from 1 to infinity an cos nx. Here you have obtained the value of an as 0. Right? So that particular term will be 0. Plus sigma n from 1 to infinity bn sin nx. Right? Now here we got the value of bn as this. Okay, when n is odd, right? So write the value of bn there, that is 2k pi n, 2k pi n. Then sin nx will be as such. Okay, so this is how you write. This is the case of Fourier series only when n is odd in the case of b. Okay, okay, then sin nx by n, then k by 2 is kept as such, 2k by pi, then expand the sin nx by n as this. So this will the it is enough, you stop it here also, no problem. After this much is enough. If you want, you can just expand. Okay, so this is the Fourier series. So you have calculated the value of Fourier coefficient a0, an and bn, and finally you substituted those values in the Fourier series. Okay, now this expression is only when the value of n is odd. Okay, now what happens when n is even? What about the coefficient b? You will get the Fourier series fx as f of x is equal to k by 2 plus 0 plus 0. Okay, so f of x is equal to k by 2. Okay, when you take n as even, because bn will be 0. Now when you take n as odd, then bn is having a value. So you can write this Fourier series in two forms. That is, one form is when bn is 0, and the other form when bn is 2k by pi n. That is depending upon whether n is even or odd. Okay, no matter you write single equation, but if you present both the results, that will be good. Okay, so you can work out similar problems. I will upload one or two problems similar to this one in LMS. At the same time, you have to work out some similar problems like this from the reference book, Satya Prakash Mathematical Physics. Okay, then okay, this is enough. So you will be given a Fourier series like this, and you will be fine to obtain the this particular expression. So what you do is study the formula for a0, n and bn, find the value of a0, a and bn, and then substitute in the Fourier series. Okay, now whenever an n comes, you can consider the two possibilities, when n is odd and when n is even, and you can present both the Fourier series. Okay, so for today this is enough. Thank you.